One of the biggest reasons that we care so much about studying groundwater is because it's such a valuable resource for agriculture and for drinking and for any other reason that we need water. There's so much water down there, it doesn't evaporate, it moves very slowly, and so it's very accessible. And generally, it's pretty clean. Um, but there are concerns that we have to factor in when we think about pumping water. When we talk about mining water, mining groundwater, we talk about pulling it out much, much faster than it can be replenished. And when you begin to mine groundwater, uh, pumping groundwater, when you begin to pull it out really, really quickly, quicker than it can be replenished, it's referred to mining. Right, so we're mining groundwater when we pull it out much faster than it can be replenished. And in fact, that's what's happening almost everywhere in the world. It took thousands or tens of thousands of years to fill these aquifers, and we have depleted them in the scale of decades to a couple of centuries. And it's going to be very difficult to adjust to not having that groundwater resource. That's sort of the longer term consequence. There are shorter term consequences for pumping all that water. And one of the biggest ones is something we refer to as subsidence. So this is a decrease in land surface elevation due to the extraction of subsurface fluids. Subsurface fluids, what does that mean? That just means stuff that's liquids that are underground, right? Mostly water, but also oil. So why does pumping groundwater lead? Why can it lead to subsidence? So this is a kind of a multi-part question, and we'll just cover the first part of it right now. So you think of a land surface here. You can imagine some point at some depth down here, just some random depth, right? And we can calculate pretty easily the stress that is bearing down on this depth, on this layer of rock from the overlying material. And we're going to call that the total stress. And the total stress is simply calculated as the height of the overlying material, the height of the overlying material, times the density of the overlying material, times gravity. And we can call that sigma. That's supposed to be a lowercase sigma t, so that's stress total, so that's total stress, is equal to rho g z, where rho is density, z is the height, and g is gravity. So that's what's pushing down. Now, in order for the rock to not just keep moving further and further down under the stress that's pushing down on it, something has to be pushing back in an equal and opposite fashion, right? There has to be these opposing forces. And it turns out that there are two things pushing back against the total stress, which is pushing down. Two things are essentially pushing up. One thing is called effective stress, which we'll do with a little lowercase sigma and the letter E for effective. So this is effective stress. Adjust this thing. This is effective stress. And effective stress is basically the grain on grain pressure. So how much is one grain pushing against another grain? How hard is that happening in order to form some sort of a rigid structure of the rock? Turns out that's very difficult to measure independently. There's something else, though, that we can measure, and that's fluid pressure. P, put a PF, that's fluid pressure. So I'll draw that down here. PF is fluid pressure. And you can measure fluid pressure pretty easily. Fluid pressure is measured as, well, let's just do an example here. Let's imagine that we drill a well right down to this layer, wherever it is, and that water rises in the well up to here. Okay, so this is all water inside the well. So the way we calculate fluid pressure is the same rho gz, but all we're doing is measuring the height of water above this layer times gravity times its density. So this is, fluid pressure is rho gz again, but now rho is not the density of the rock, it's the density of water times gravity times the height of water in the well. Right, so it's the same as fluid. The pressure head. Right, this would be the pressure head from the calculation of hydraulic head. So what do we know? Well, we know that the total stress total, that's the downward force, has to be equal to the effective stress plus the fluid pressure. And since we can calculate this pretty easily and we can calculate this pretty easily, it's not too hard to solve for. Whoop, I think I might have gone off the page there. Let's try that again. Since we can, so here we are again. Total stress, sigma T, is equal to effective stress, sigma E, plus fluid pressure. Since we can calculate total stress pretty easily, we can calculate fluid pressure pretty easily. If you have two of the three variables in an equation, you can solve for the third. Okay? So this is a little thought experiment that's going to lead us to the next part of this discussion with respect to subsidence, which is this. What happens if you have a constant downward stress, right? You're just looking at the rocks buried at some level, so the total stress is staying constant. And the total stress, which is the downward force, is being borne by, again, these two upward pushing forces, the fluid pressure and the effective stress. The effective stress is how hard each grain is pushing against its neighbor grains. And the fluid pressure is what the pressure of the fluid is in the pores. If you begin to dewater the aquifer, if you begin to mine the water out of the aquifer, what's going to happen to the fluid pressure? If you take water out of the water balloon, what's going to happen to the water pressure? It's going to go down, right? So if the fluid pressure goes down, total stress is staying the same. This is going to go down. What has to happen to this? If you dewater an aquifer, and this is primarily confined aquifers, if you dewater an aquifer so that this value decreases and this value stays the same, this value has to increase to compensate. So that means that the grains are going to be pushing against each other harder and harder and harder, and they're going to pack themselves into a tighter and tighter configuration. And what does that mean? That means that the aquifer is going to compress. And if the aquifer compresses, it's going to be taking up less vertical space. So the land surface over the top has got to subside. The land surface is going to shrink. It's going to fall in elevation as the rocks below it begin to compress. And why do they compress? Because we've taken water out of the aquifer. We'll see specifically how that works in the next video.